Hey Kennedy, hi Connor, hi Zane, hi Jared. I told you by the end of semester you'll know me more or less. Main thing is just to come to the lab today. And here, just lean back, relax, and I'll entertain you with more equations if you consider this entertainment. Last time we did discrete representation for coherent, for eigenstate of annihilation operator. Today we will do it in the continuous representation, and by looking on two solutions, we'll get some insight what happens with the excited oscillator, which means interatomic bond that was irradiated by infrared laser or excited from ground to advanced excited electronic state by UV pulse. So here is the 2 days ago I thought it is expected outcome of number 34. Now it is expected outcome of 35. So we are going to obtain probability distribution for excited harmonic oscillator for eigenstate of the annihilation operator. So note that this letter P is different from psi. As we go towards this stuff, we will compute psi and then take it absolute value square and get P. This thing that we are going to get is very similar to the ground state of harmonic oscillator, to the state number 0, which I'm independent in the equation. It's exponential, it's centered Gaussian, and the only difference is that instead of being centered on the equilibrium bond distance, it is centered on the thing that changes over time. And the thing that changes over time will include the frequency of the oscillator and time. The notation as we go will be changed, and I'm doing it because I was using different sources, different books. So just giving you a heads up, whatever I was calling mu for the last 2 weeks will be called gamma. Okay, so if we arrive to this equation, the goal will be achieved, and I have slides to go a little bit further into the material, but if time allows. So we are returning back to the intuitively comfortable, as well as any equations can be comfortable for human. Intuitively comfortable representation where wave function is defined as position, continuous position, and we do have the annihilation operator that acts on the unknown wave function, gets eigenstate and unknown wave function. So it shouldn't be a big surprise. In some sense, we already know the answer. We know the answer in terms of expansion over eigenstates as a series. Right? Ground state plus first state plus second state with certain coefficients will give us the solution. But the goal or the reason why I'm doing it and inviting you to follow me is that in the continuous distribution, it has some symmetric form that is comfortable to analyze. So if we plot the result in either of the methods, we'll get the same thing. But for analysis, comparison of these two approaches looks healthy and beneficial. So, annihilation operator is adding together position and momentum, right? And momentum is derivative over position with h bar and image degree. And just in case this was derived in order to reproduce the Hamiltonian by a dagger product. So if one wants to check that dimensions are correct, after taking this and this squared, it should give the potential energy m omega squared x squared over 2. So in the past, we did practice the very similar equation as our bypass way to get the ground state of the state. So we were looking on the same equation where eigenvalue equals 0 and the whole right part is equal 0. So we were looking on applying annihilation operator to a unknown function that gives 0. So straw man tries to commit a suicide and jump down from the lowest state. The differential equation that we are going to solve today is not much more complicated. So this A was containing the independent variable and derivative. And now we will have independent variable once again. So it should be doable, even without any computers and even without taking the differential equation. So change of notations. It would be possible to do everything without changing, but since I was using one of the texts as a cheat sheet, it was a headache to change it in any way, so it's simpler to solve. One of the observations at the end of the last meeting, so probably will focus. Tell the story. So when we were here 2 days ago, we solved this problem in the discrete representation. We obtained the expansion coefficients, which ramping up the coefficient in front of any eigenstate has nominator with eigenvalue to the power n and denominator with square root of n factorial. And then we did use the principle of predicting future through expansion coefficients, where each eigenstate evolves forward in time by accumulating phase, right? Through this imaginary expansion. And it accumulates phase, the quicker, the higher the energy. When we did practice this trick, we found that due to the special symmetry, special form of the energy spectrum of harmonic oscillator, which some people call it equidistant. So the distance offset of each state is the same. So due to this property, one was able to treat the accumulation of the phase the same way as one was treating the eigenvalue to the power n. So it was exponential that accumulates phase with space equals to frequency of oscillator omega times n, or e to the power minus I omega t brackets to the power n. So we combined eigenvalue of the annihilation operator and accumulation phase into one thing. And then we observed, Jared agreed with me 100%. Zane expressed some concerns that maybe normalization factor may have some issues. and I promised that we can look on it later. But one of our observations that the replacement of the eigenvalue from time-independent part to the time-dependent part by accumulating phase and putting it inside the eigenvalue, one is reproducing functional form of the eigenstate of annihilation operator. So in some sense, we obtained the result that this summation of expansion coefficients time eigenstates where eigenvalue is time dependent, is rotating in the complex plane, will be always eigenstate of annihilation operator. So both eigenvalue and eigenstate of annihilation operator are time dependent. Very different from eigenvalues of the energy operator, which are static. The eigenstates and eigenvalues of the annihilation operator are dynamic. They just evolve. The slide that is offered with this ugly handwriting and with substitution of mu to gamma reflects the same story. So the eigenvalue of annihilation operator evolves in time by accumulating phase. Why do we need it and how are we going to use it? I can play open cards. So first we'll solve differential equation. Second, we will take the solution absolute value squared. So wave function times itself. And in the wave function, there will be exponential with some stuff, and then there will be gamma, this thing that is on the board, times x. And when we multiply, when we take absolute value squared, we will get complex conjugate of the gamma, which makes rotation of this phase accumulation in the opposite side. And when we multiply these things together, there will be summation of exponentials evolving forwards and backwards. And then by Euler equation, this imaginary exponential will combine into cosine. And this cosine will turn into the center of the Gaussian. Make sense? So basically, I completed whatever needs to be done today. But just in case some of the class attendees are watching it in the record, I'll just show slides. Okay. There is nothing new in this slide. There are only manipulations with equations. And here is quiz that I always planned to do in this class, but maybe I'll forget to do it. So the arrangement of the quiz is as follows. One writes boxes, leaves empty spots, and asks everyone in the class to fill in. I'm a little hesitant to do it because I'm not sure that I will be able to do it myself without a cheat sheet. I can read it really, but not memorize it. But if our goal is to convert into the differential form, we just replace p with minus I h bar ddx, derivative of the space. Imaginary units will compensate each other. And then we can play with the factors. So we can bring this factor from outside of the bracket inside. And then there will be an interesting observation. So the factor outside has square root of mass and omega in the denominator. X has mass and omega in the numerator. If we combine these two things, we will get mass and omega in the numerator. Okay? If we bring this factor in front of derivative, we will keep the mass and frequency in the denominator. So by looking closer onto this expression, they look symmetric. So it's square root of mass and mass omega divided by Planck constant, and here is Planck constant divided by mass and omega. So it looks like inverse of itself. And this is a way to make the notation shorter, which is just a tribute accepting the principle of laziness, which is in classical mechanics is called the least action principle, and for between humans, laziness. Like the lesser the number of symbols I write, the happier I am. So this square root of Planck constant over 2 mass and frequency will be sigma, and it's natural because it will be related to the width of the distribution. And then by using the substitution, the initiation operator will be 1 over sigma times position, and then sigma times derivative. So there are not too many people who are happy, who get joy out of solving equations, if it is not correlated by any form. But if one has to solve equations, this as part of the differential equation is not too bad. So it's short enough, simple enough, it has only 3 variable and derivative. So I'm going to apply this stuff to a known function and equals to eigenvalue times a known function. In one hand, it is all self-evident, but on another hand, if any of us will be watching, it will be very boring without comments. So, first thing in the brackets, it is an equation operator, right? An unknown function, then eigenvalue that before was mu, now is gamma, and an unknown function. So how can we solve such equations? What is the plan? Or how can we interpret what is done in the next lines? There are advanced methods to solve differential equations, but we want to live a simple life. And the best way, if one can separate dependencies of free function with all derivatives on one side of the equality sign, and so function on one side, argument on the another. Then integrate both sides. So if we divide each term by unknown function and multiply each side by dx, there is a chance to remove dx here and has psi here. So this term will have only function. Remove psi here and have dx, making it function of making it only independent argument. And here we will cancel function and we will have just dx. Then one can either reorder them, or first integrate and then integrate, or first integrate and then reorder. So 1 over 2 sigma x dx comes from this term, right? D psi or psi comes here, same as non-trivial. And we already know that it will be logarithm, right? And here we have just this eigenvalue and then integral of dx. I think I have forgotten to make regular questions to online attendees. Let me check it now and then we'll go further. So, question to Kennedy and Connor, if there are any suggestions, questions, complaints about the content, or if you are fine with the content. Okay, thank you, Kennedy. Okay, I'm going to share and go forward. So, integral of x dx is x squared, integral of psi is logarithm, integral of x is dx is x. And then we can divide left and right by sigma. So it will be sigma squared in the denominator here, no sigma here, and 1 over sigma here. So what is my next step? I want to combine function in one, let it be on left, and then transfer this x squared term to the right with minus sign. I think last years I was practicing to rederive. Oh, I see. Zain is you're deriving yourself, right?
Yeah, I'm trying to.
Good. It's a good exercise, and there is a more or less guarantee of success. It's a beautiful thing. So, logarithm on left, polynomial on the right. Oops. So if we place left and right sides into the power of exponential, nothing happens, right? It's permitted operation. So exponential of logarithm will be just this function over its value at 0, initial value, and here it will be exponential of all this stuff. And then we multiply left and right by this same. So wave function of x is wave function not initial value, and then we do have exponential of polynomial. So what is very healthy and good that we have minus in front of x squared. It means that it will be, again, Mexican sombrero. As argument goes plus infinity or minus infinity, the function will get to 0. So it is a good normalized function. What is different from our previous exercise about a month ago for eigenstate of Hamiltonian for the ground state? We do have this additional term, right? It is only the first power of the independent variable. The first power main property of polynomial is defined by the senior power. So if we made a conclusion that this minus x squared will make this hat shape, it will be not changed by junior power. But there will be some additions. So we will need to process and explore what would happen to this exponential due to this additional term. and we will need to take into account that this gamma is time dependent. It's not a big secret. So adding additional linear term to polynomial will shift equilibrium position. One just needs to take it carefully. Yeah, if you hate ugly handwriting and you like type things, here it is. I can take your input if you're sure that you like type things. You can help next generations, and I will erase handwritten things and just show this one next year. And someone likes to solve this equation again and again. Well, we can shift the center of the distribution right away for the wave function, but it is not our goal. The camera, the wave function itself is not an observable. Probability distribution is not typically an observable, but it's something intuitive that we can analyze and relate to real world. And originally we were planning to focus on the probability distribution. I suggest we go right away to probability distribution and make this shift of the center right there. It will be quicker, easier, and more relevant, rather than to waste time on the wave function. And the plan, and you can, as I'm speaking, you can see it on the slide. The plan is to take wave function and then wave function conjugated, which is symbolized by the star. And the star conjugation means that anywhere you observe imaginary unit I, you swap sign in front of it. And this rule holds very generally. You do not need to care whether it is I is nominator, denominator, power of exponential. Just swap sign of any I that you see in the equation, and it will be correct. So here will be one more notation that is not mine. And if you hate it, I can provide you names of the authors of the book who is guilty for this notation. But after admitting it, the derivation becomes really quick, and I cannot do better. So the novelty is that they chop the time dependence of this gamma, which is eigenvalue of annihilation operator. So the factorized chop represented in a special form. So there is initial value, then this time dependence, but there they not simply do the frequency and time. They add initial phase, just to speak about the instant of time, what was phase of the wave function when time was equal to 0, when we started this oscillations. How does it relate to real life and physical chemistry? If we have a train of pulses, if our lasers are synchronized and we do one pulse after another one, and we can tune them by the fraction of the oscillation period, then there are some experiments that are phase sensitive. And right now we are just doing it to be general and give the answer for any situation, because initial phase can be different. Later on, when we need just to make an example, we can set rho equals 0, but now we do not want to lose generality. And sometimes if I want to replace 1, 2, 3, 4 symbols by 1, I will use the letter theta as a time-dependent phase. So gamma without star, gamma not E plus I rho, no, plus omega T. Gamma star, we just place the minus sign in front of it. Now, the definition of the probability distribution is wave function star times wave function. So we multiply e to the power, and then the thing that we got on a couple of previous slides. So x squared x, gamma over sigma, sigma squared. And here, the only thing that we put little star on the top of gamma, because x and sigma are real, and we do not need to apply star conjugation to them. So basically, in the remaining time, we are going to multiply these two exponentials and make sure that we carefully treat this gamma and gamma star. Why are we doing it? Because we hope to convert these exponential forms into cosine and get it as the moving center of the distribution. So multiplying two exponentials is equivalent to adding together their powers. Right? So flipping back once again. So x squared over 4 sigma, going forward, x squared over 2 sigma, sigma squared. So just adding together. And then 1 over sigma gamma x, 1 over sigma gamma star. So we're just adding together this gamma and gamma star. So it's time for our old buddy Euler to help us, because this gamma and gamma star are two exponentials accumulating phase in the opposite directions. And according to Euler formula, we can always convert it into sine and cosine. So adding together this gamma and gamma star is adding together e to the power I theta, e to the power minus I theta. And according to the Euler equation, this e to the power I theta minus e plus e to the power minus I theta will be just cosine theta. Make sense? Let me check this online part of the class that no one lost me and the narration story. That things make sense. Canadian Corner, if you got any questions or doubts in the story, please let me know. The lack of answers is treated as you're feeling brilliant and additional comments are not needed. Any questions? 1? Any questions? 2? Any questions? 3? Okay. Continuing to share screen and telling the story. Yeah, thank you. So wherever we had this gamma plus gamma star, we will replace it by 2 gamma naught cosine theta. And theta can be replaced by rho minus omega t. So it will come into this term. So we are almost there, but not yet to the full extent. So we got x squared minus x gamma naught cosine of this stuff, initial phase and then phase accumulation. And the only thing that we need to complete is to carefully treat the shift of the center that I declined to do for wave function, but now it is time to do it for the probability distribution. So a linear term, linear in this free variable, must give a shift of the center of this distribution. So what I am suggesting to do is to consider stuff in the brackets as simplest algebraic formula, like square of the sum. So we need to identify full square, like a squared plus 2ab plus b squared. Those are three terms, and we have only two. But by the rules of math, nothing is changing if we add and subtract an additional term, if we did the same term. So if we treat this x over sigma as a, and x squared over sigma squared will be a squared, then we can identify that the second term has has the stuff that we can call a, and then the rest, this 2 gamma naught cosine rho minus omega t, can be treated as b, right? So if we define this as b, we can just add and subtract it. And as soon as we have a squared minus 2ab plus b squared, this will be a full square that we can identify and treat as Gaussian with traveling center. As a price for it, we will have additional factor, e to the power minus b squared. This will not change shape of the function. This will not change the center of the function, but it will change absolute value. So it will be normalization which is time dependent. So as a price to this little trick, you will get time dependent normalization. It should be on the next slide, but through this b, we will get e plus 1/2 b squared as a continuous factor at the front, and it will be time dependent. So overall, the function will be a little taller and a little lower as we move forward. So here is the full square, a minus b squared. So position minus traveling center squared. So this is Gaussian shape that moves forwards and backwards. And this is the dynamic normalization. But if we carefully continue, which I'm not going to do, then one can find that this normalization factor C star C will be also time dependent, and they are going to cancel this stuff, and things will be quite simple. So I think we did arrive to the posed goal, and one day, maybe tonight, maybe on the next lecture, some of us, either me or some of you, may show, I think it was on the presentations too, how the initial Gaussian wave packet moves in the oscillator, right? Just the same shape moves forward and backwards. And if the width is not ideal, then you have seen that it gets tolerant and lower. So you already saw this thing yourself. So let's give this 2 minutes to you for travel to other things, because we need to accumulate strengths for tonight. So meeting is done. Everyone is welcome to depart.